As a quick warm-up, we're going to graph y equals 2x plus 3. So we start on the y-axis at 3, we rise 2, run 1, rise 2, run 1, or fall 2, go left 1, and we have our equation of our line. To find its inverse, we can simply reverse the points. 0, 3 becomes 3, 0, 1, 5 becomes 5, 1, and 2, 7 becomes 7, 2. And so forth, or go left 2, down 1, left 2, down 1, left 2, down 1. And we can tell these are inverses of each other because they are a reflection across the line y equals x. So today we're going to talk about logarithmic functions and their graphs. And thus far we've been talking about exponential functions. Exponential functions are functions that go through the point 0, 1, because anything to the 0 power is 1. And then based on their base, if this one happens to have a base of 2, because when x is 1, y is 2, 2 to the first is 2, 2 squared is 4, and so forth. Has an asymptote on the x-axis. So we're going to find that if we want the inverse of it, a logarithmic function, our asymptote will be the y-axis, and it will also have a common point of 1, 0. So logarithmic functions are defined as y equals log base a of x if and only if a to the y is equal to x. So thus far we had been working with y equals a to the x exponentials, but x equals y a to the y is just wrote this here. X equals a to the y is the inverse of that. We've switched the x and y around. Now this is provided that both a and x are positive and a is not equal to 1 because anything 1 to any power is still itself. So the way to remember how logs work is to remember that the answer to a logarithmic equation is the exponent of the exponential equation. The answer to the logarithmic equation becomes the exponent of the exponential equation. So if I ask you to write the following in exponential form, we want to say if log base 10 of 100 is 2, my base is 10, so 10 to the answer to the logarithmic equation is going to be the exponent. So 10 squared equals 100. This will always be true. We should not give you an equation that is nonsense. So if you try to convert it to an exponential form and it doesn't make sense, you've done something wrong. Likewise, log base 3 of 81 equals 4 should say what? 3 to the 4th equals 81. Let's go backwards. If we have to write an exponential into logarithmic form, remember that the answer to the log is always the exponent of the exponential. So 8 is the answer to the log, and it's log base what? Well, the base of the exponential is the base of the log. Log base 2 of 256 is equal to 8. How would 5 to the 3rd equals 125 be written in logarithmic form? Log base 5 of 125 equals 3. 5 to the answer to the log is equal to 125. And how would 17 to the 0 equals 1 be written? Log base 17 of 1 is 0. So properties of logs. Log base a of 1 is equal to what? Well, a to the 0 equals 1. So the log base a of 1 is 0. Anything to the 0 power is 1. And log base a of a is 1 because a to the 1st is equal to a. And log base a of a to the x is what? A to what power has to be equal to a to the x? it's x. And finally, if the log base a of x is equal to the log base a of y, then a to some power has to equal x, a to some power has to equal y, x has to be equal to y. So the question to ask yourself as you're working through these is base a to what exponent is? For example, if I want to solve log base 4 of 16 equals what? Base 4 to what exponent is 16? 4 to what power is 16? 4 squared is 16. Log base 6 of 1 is what? Base 6 to what exponent is 1? That would be 0. 6 to the 0 equals 1. Log base 9 of 3 is what? 9 to what power is equal to 3? We learned the one-to-one property that said that if you can get the bases the same, then the powers are the same. So what would I have to do to 9 to make it into a 3? I'd have to square root it. So if I'm square rooting 9 to get 3, the power of the square root is 1/2. And log base 2 of -1 is what? A positive 2 to what power can get me a -1? That's nonsense. 2 to no power can become negative, so this is undefined. Because a few slides ago we mentioned that anytime we're taking a log, that where the log base a of some number, x has to be a positive number. All right, so exponentials versus logarithms. When we were graphing exponentials, I mentioned that because exponentials grow so much and we are limited in our graphing space, that we have to be able to at least give 2 points in an asymptote. So our 2 points in our asymptote are always the common point of 0, 1, and then the base point based on what the base is. So if it's a base 2, we're going 1 over and 2 up because 2 to the first is 2. If it is a base 5, we're going 1 over and 5 up because 5 to the first is equal to 5. So they all look similar, but they'll be slightly changed. Some are more steep, some are more shallow. And all of exponentials, until they've been moved, have a common asymptote of the x-axis, or y equals 0. So what would a logarithm look like? Well, since these are inverses of each other, if we were to sketch the logarithmic graph, we should be able to reverse points. So our 0, 1 should become a common point of 1, 0. And our base point of 1a should be a 1. And our asymptote that was the x-axis should now become the y-axis, and so we should have a graph that looks similar to this. So you have a sheet that looks like this. It came with your packet, the notes sheet. And I want to show you 3 different ways that you can graph logarithms. And honestly, the first method is the one that I used my very first year of teaching pre-calculus, and I wish I could go back and apologize to my students because it's not the most efficient, but it made sense to me at the time, and it is a very valid way of doing it, but it's more tedious than the second 2 methods. So we'll walk through the first one, and then I'll explain why it works, but I think you'll prefer the second or third one. So when we're converting f of x equals log base 3 of x plus 1 minus 2 to an exponential so we can graph it, that's the method I initially started with. And so that said that if y equals log base 3 of x plus 1 minus 2, and I want to convert this to exponential, I first have to get the log by itself. So I would add 2 to both sides. So I have y plus 2 is now equal to the log base 3 of x plus 1. Now remember, the answer to the log is the exponent in an exponential. So 3 to the y plus 2 is now equal to x plus 1 if I'm solving this. Or converting it to exponential, now I'll solve for x. So 3 to the y plus 2 minus 1 is equal to x. That's how I got my equation for my t-chart. Now, this is what's odd, and it feels strange, because we need to plug in numbers for y in order to figure out what's going to happen to x. So this is our x now, and that's our y. And we have to pick good numbers, because if we picked a number like 1, we would be taking 3 to the 1 plus 2, or 3 to the third, and getting 27 and subtracting 1, and we're now at 26, and we don't have room on our graph to graph 26 comma something. So, or 26 comma 1. So in this case, then we would pick some nice numbers that will make this something that we can graph. And again, this is not the most efficient method, but it is a method. I'll let you read through it and play with it if you want. If this is a method you prefer, you're welcome to use it, but I'm not going to spend a lot of time on the rest of it. We'd just be plugging in these points, and then once you get ready to graph, it's normal and natural, but it seems strange or odd to put in values for y and to figure out what x is. So here's our second example, a second way of doing this. So you can graph the parent of this function, and then you can translate it. So we know that if f of x is equal to the log base 3 of x, we would get the parent function. And then the plus 1 is going to translate this left one, every point and the asymptote. And the minus 2 is going to translate this down 2. And so we can pick nice values that we know how to find the log of, and then plug them in and figure out what the values are. So we know how to find the log base 3 of 3. So when x is 3, the log base 3 of 3 is 1, because 3 to the first is equal to 3. And we can find the log base 3 of 9, so we could say 3 to the second power gets us 9. We can find the log base 3 of 1, 3 to the 0 power gets us 1. And we can find the log base 3 of 1/3 and 1/9. 1/3 will be a negative 1, because 3 to the negative 1 is 1/3, and 3 to the negative 2 is 1/9. And now we can plot those values for x. When x is 3, then y is 1. And these are by halves, so be careful as you graph these. When x is 2, y is 9. We're already off of our screen here. Sorry, when x is 9, my fault, y is 2, so we're going to be over here somewhere. And when x is 1, y is 0. And when x is 1/3, so 1/3 of the way over, y is going to be negative 1. So there's a half, this is roughly a third. Here's a 9th at negative 2. And we're going to get really close, 1/27th, 1/81st. So there's that asymptote that did not graph those well. 9, I advanced the slide accidentally. You'll get the idea though. When x is 1, y is 0. When x is 1/3, y is a negative 1. And when x is 1/9, y is a negative 2. So we get a graph that looks like this. However, if you are comfortable with functions and how inverses work, then with an exponential function and how inverses work, then you can graph this much more efficiently. And we can do that by saying, all right, I know that if I'm working with the log base 2 of x, my asymptote is going to be x equals 0, or the y-axis, on all of these, because the inverse of a log is an exponential, and the exponential had the horizontal axis, y equals 0, or the x-axis as its asymptote, so we're just flipping it. But our common point is always 1, 0 with logs, because we said anything to the 0 power was 1 on an exponential. That means that if an exponential has 0, 1, its inverse, a log, is going to have 1, 0. And log base 2 of x will have a base point of what? Well, 2 to what power gets us x, or 2 to the, when x is 2, y is 1. 2 to the first equals 2. If we're looking at log base 3 and we want our base point, then we would go 3 over 1 up. Our base point of 4 is 4 over 1 up. And our base point of log base 5 is 5 over 1 up. So because this is a log base 3, shift it again 1 left and 2 down. Then we can plot our original base point of 1, 0, our common point, and our base point of 3, 1. And we can take those 2 points and we can translate them, and we're going to translate them left 1 and down 2 in addition to our asymptote. So our asymptote was the y-axis. If I go left 1 and down 2, I can't really tell that it's gone down 2, but I can tell that it's gone left 1 because it's 1 to the left of the y-axis. And then I move every point left 1 and down 2. There's my common point. Left 1, down 2. There's my base point. And because this is a nice number like 3, and we're moving it to the left, when we are 9 over, we would have been 2 up. 3 squared is 9. And so when we're moving left 2, we'll be at 7. And we would have been at 7, 2. But we're going, or 9, 2, we're going to be at 8, left 1, down 2, at 8, 0. So we can get more than 2 points in an asymptote on this one because we do have space. But 2 points, 1, 2, common point, base point, and the asymptote is sufficient. So let's do one more example. Log base 4 of x minus 3 plus 1. Decide which method works best for you. Probably not the first method of having to convert this to an exponential first, then picking values for y to plug in to find out what the values of x are. But you could say, I know how to find the log base 4 of 4, and I know how to find the log base 4 of 1, and I know how to find the log base 4 of 16, but it wouldn't fit on my graph, so I could find the log base 4 of a fourth. I could find the log base 4 of 1/16, and those are my x values. Figure out what the y values are, then translate it 3 right and 1 up. Or we can say, I know I'm going to have a common point of 1, 0, and that 1, 0 is going 3 to the right. So 1, 2, 3 to the right, and 1 up. So here is my new common point. My base point would be 4, 1. So I'm taking that 4, 1, and I'm moving it 3 to the right and 1 up. And my asymptote was the y-axis. I'm moving it 3 to the right, and we can't tell that it's moved 1 up because it's a vertical line. And we could graph our 2 points in our asymptote. All right. Natural log. We know that E is roughly 2.718281, an irrational number. It is the base of a natural log, and we call it the natural log. So the natural log is log base E, which is log base 2.718. So if we're graphing y equals the natural log of x, the easiest way to do this is to find your common point and your base point. And your asymptote. And graph them. So my asymptote is the y-axis, x equals 0. I have a common point of 1, 0. Apologies. And a base point of 2.71, 1. And then I sketch my graph. 2 points and an asymptote. If I need to graph y equals negative natural log of x minus 1, I know I'm going to reflect across the x-axis. And I'm moving 1 right. So my common point of 1, 0 and my base point of 2.71 is where I'm going to start. And if I'm moving 1 to the right, my asymptote will be 1 to the right. I want it to be at 1, 0, but now I need to move that point 1 to the right. I want it to be at 2.71 to the right and 1 up, and now I have to move it 1 to the right. But the reflection says reflect across the x-axis, so I would be negative 2.7 or 3.71, negative 1. And now my log looks like this. Anything that was above the x-axis is now below. Anything that was below the x-axis is now above. All right, so the last thought is how to solve something. Well, a moment ago we said if the log base a of x is equal to the log base a of y, then x has to be equal to y. So since the log base 12 of x minus 3 is equal to the log base 12 of 2x plus 5, then x minus 3 should be equal to 2x plus 5. Solving this, we'll subtract x from both sides, and we get x. Subtracting 5 from both sides, we get negative 8. Which seems simple enough until we realize that if we plug this back in, log base 12 of negative 8 minus 3 is going to be log base 12 of a negative 11. 12 to what power can get me a negative? A positive number to what power can get me a negative number? There isn't one, so this is actually no solution. So be sure to check your domain. Remember, we said there were 3 things that we weren't going to be able to do this year, and that is to divide by 0, to take an even root of a negative number, and to take the log of a negative number. So if we happen to get a negative number when we're solving these equations, we have to say no solution. Last example, since the log base 3 of x squared plus 4 equals the log base 3 of 29, we can't change that to an exponential. We just say x squared plus 4 is equal to 29. So if we subtract 4 from both sides, get a 0 pair, x squared equals 25. The inverse of squaring is square rooting, and when we introduce the square root, we introduce a plus or minus, so x is equal to plus or minus 5. So we suspect that maybe negative 5 won't work. We plug it back in, and the log base 3 of negative 5 squared plus 4 does get us 29, so both positive and negative 5 work. Your assignment is a book assignment and the 2 points in an asymptote logarithms assignment in your packet. So make sure you do these problems. They're all required on page 218, plus the 8 quick graphing problems that you see in your packet. Let me know if you have questions. I'm here before and after school.